We are going to see the derivation of torsion equation. We know that torsion equation as T by J is equals to tau by R is equals to G theta by L. Here T is the torque applied on the shaft, J is polar moment of inertia, tau is the maximum shear stress at the radius of R, means topmost layer, and G is the modulus of rigidity of the material, and theta is the angle of twist, and L is the length of the shaft. Here we can see here this is the L, that is the length of the shaft. Let us see the derivation. So from the first diagram A, so we can write here the shear strain phi is equals to B dash by AB. How we can write this as means, we know that from the basic definition of shear strain, suppose if you take a block like this and if you apply a force on this surface, suppose it is ABCD. So when you apply this force parallel to this surface, this is called shear force, and because of this shear force, this ABCD plane will be deformed to like this. So this B is occupy new space B dash, and this is called phi, that is called, we are calling this as a shear strain. And if you write the shear strain formula here, it is equals to B dash by AB. So from this we can write here also shear strain in this plane as phi is equals to B dash AB. And here suppose if I write for B dash, that is phi into AB, but AB is nothing but length of the shaft here. So this can be written as, so this is the side view, but here AB will be the length of the shaft, clear. So this is phi into L, that is B dash. So let us take it as equation number 1. And if you see from the second diagram B, suppose if I write for B dash, this will become the arc length. That arc length is given by r theta, and this is equation number 2. So because 1 and 2 are both are giving B dash, so 1 is equals to 2. So I can write here phi into L is equals to r into theta, and this from this I can write phi is equals to r theta by L. Let us say this is as equation number 3. And also from the basic definition of shear strain, I can write shear strain as shear stress into by modulus of rigidity. How we can write this means, we know that modulus of rigidity G is equals to tau by shear strain, means this is modulus of rigidity shear stress by shear strain. From this if you write shear strain, this will be tau by G. So we have written the same thing, shear stress by modulus of rigidity. So in terms of symbols, it can be written as tau by G, and this is shear strain phi. This is equation number 4. And if you compare this equation number 3 and equation number 4, both are giving the phi only. So once again we can equate 3 is equals to 4. So from that we can write here tau by G is equals to r theta by L, and we can write here tau by R is equals to G theta by L, and let us say this as equation number 5. So see here, for the given shaft material, G is constant, and for the given angle of for given torque applied, theta is also constant, and length is for given shaft, length is also constant. So for a given shaft and for a given amount of torque, all these three are constant. So we can write from the above equation tau by R is equals to constant, such that, so here I told already tau is the maximum shear stress produced at the radius of R. Suppose we take some layer at the radius of small r, let us say small q is the shear stress produced in this layer at the radius of small r, and I told this tau is the maximum shear stress which is producing at the capital R. So from this relation tau by r is equals to constant, I can write q by small r is equals to tau by capital R is equals to constant. And here so this next, if you proceed with this, let us consider a small differential layer on the shaft which is at the radius of small r, and this area of this differential element is dA, and let us write a shear stress on this element as small q. And from this we have already shown that we have already came to know that this is can be written as small q can be written as tau by r into small r. So this is the shear stress on this smaller element, and if I write force, that is small amount of force on this element, that is stress into area, means q into dA. In the place of stress, that is I can write tau by r into small r into dA. So this we have written from the formula: stress is equals to force by area, and force is equals to stress into area. So here we have written stress as like this. So force is stress into area. The stress value we have written from this equation like this. And if I write torque on acting on this smaller element, that is, let us take dt, and this torque we know from basic definition, torque is nothing but a force multiplied by this distance between the axis of rotation and this application point of application of force. Simply we can write F into R. So if I write smaller torque means smaller force into this radius, so I can write here this force multiplied by this radius value, and this force we can write from this previous one, tau by r into small r into dA into this r. This is the force and this is the r, and this r into r, it is nothing but r square dA, and here this is the torque acting on this smaller element. Suppose if I want the torque or total torque value, we should integrate here. So this is the integration of dt and integration of tau by r into r square into dA. So because tau by r is a constant, I can write outside tau by r integration of r square dA. So this the term integration of r square dA is called polar moment of inertia. So we know that suppose if I take a simple rectangular element like this, and if I take a elemental area, and if I suppose if I write from the basic definition of moment of inertia, I, that is distance square multiplied by the area. So distance is a y, so it is y square into dA. Integration of y square into dA will give the moment of inertia. In the same way for the shaft, this is at the radius of r. So and this is the elemental area dA. So if you write integration of r square dA is nothing but moment of inertia about this polar axis j. So finally we can write this integration of r square dA as j, and this integration of dt is t. And from this one we can write t is equals to tau by r into j. Suppose if I write t by j tau by r, and also this is the equation number 6. And suppose if you see, if you compare the equation number 5 and equation number 6 here, so which is having this same tau by r and tau by r, and if you compare and if you write here compare equations 5 and 6, so we can write finally t by j is equals to tau by r is equals to g theta by L. So this is the torsion equation. So for more videos, please subscribe and like it, share it. Thank you.